Bioinformatics Micromodules, Mutation Model. In this module, we describe a formal probabilistic framework for defining the evolutionary distance between sequences. The concepts will be useful when we discuss maximum likelihood methods in the next module. To begin this module, suppose we have two aligned DNA sequences that differ only at the third site. Now suppose these sequences were originated from the same ancestral sequence. What nucleotide did this ancestral sequence have at the third site? Of course, we don't know, unless we can travel back to the past or have a record of the ancestral DNA. Let's assume the ancestral sequence had nucleotide A at the third site. Now our question is, how many mutations have happened to this third site since the time of the ancestral sequence? One possibility is that only one mutation has happened, which changed the A to a C. This is the most parsimonious explanation of the two observed sequences. However, there are also other possibilities. For example, the A could have been first mutated to a G before it was mutated again to a C. Since we can only observe the two current sequences, we cannot observe the intermediate G, which has already been overwritten by the C. There are also other possibilities, such as the A was mutated to a T before mutating to a C, or on the left sequence, there was actually a mutation of the A to a C before it was mutated back to an A. In fact, there's an infinite number of possibilities to consider. If we know the actual number of mutations happened to the two sequences since their divergence, this mutation count can be used as an evolutionary distance between the two sequences. Since this actual number of mutations is not known, we will use a probabilistic framework called a mutation model to consider all possible mutation sequences. To make computations simple, we will make several assumptions. First, we assume that different sites are independent, such that we can consider each site separately. Second, we assume the rate of mutation is the same for every site, and that this mutation rate does not change over time. For example, if the mutation rate is 1 mutation per year on average now, a million years ago, on average, there was also 1 mutation per year. Finally, we assume that if we know the current state, future states do not depend on the states in the past anymore. This is called the Markov property, which limits the temporal dependency to the nearest event. These assumptions are in fact not correct, and there are models that do not require such strong assumptions. However, in this module, let's stick to these assumptions such that we can discuss a simple mutation model. The mutation model that we are going to study was described in an article by Thomas Jukes and Charles Cantor in 1969. This model assumes that time can be discretized into small units. In each time unit, at most one mutation can happen at each site. This assumption is actually not a big problem, because we can always make the actual time corresponding to each time unit shorter, to the extreme of an infinitesimally small duration. This model also assumes that each nucleotide has an equal chance of alpha to be mutated to each of the other 3 nucleotides within one time unit. Correspondingly, the probability for a nucleotide to remain unmutated in one time unit is 1 minus 3 alpha. To illustrate how the Jukes-Cantor model can be used to compute probability of a mutation sequence, let's assume that at time 0, a certain site of a sequence has nucleotide A. At time 1, what could the nucleotide be, and what is the corresponding probability? As just explained, there is a probability of 1 minus 3 alpha that this nucleotide remains A, a probability of alpha that it is mutated to C, a probability of alpha that it is mutated to G, and a probability of alpha that it is mutated to T. Now it becomes more interesting if we consider time 2. What is the probability that the nucleotide is A at time 2? As discussed previously, we need to consider all possibilities. The first possibility is that the nucleotide was also A at time 1, and again it was not mutated from time 1 to time 2. The probability for it is the square of 1 minus 3 alpha. The second possibility is that the nucleotide was something else at time 1, and it was mutated back to A from time 1 to time 2. The probability for it is 3 alpha squared, which is the total probability of the mutation sequences A to C to A to G to A, and A to T to A. Therefore, taking the two possibilities together, the total probability that the nucleotide is A at time 2 is the square of 1 minus 3 alpha plus 3 alpha squared. In fact, we can continue with this calculation to ask the probability for the site to contain a particular nucleotide at any time. One issue of doing that is that if we want to know the probability at a certain time t, we need to repeat the above type of calculations t times. Remember that we want to make each time unit small, which would equivalently make the number of time steps large, and thus the calculation time-consuming. Therefore, instead of doing it step by step, we want to derive a formula that can easily tell the probability at any given time t. To do that, we need to set up a recursive formula. First, we define a symbol px to y bracket t to indicate the probability that a site contains nucleotide y at time t if it had nucleotide x at time 0. For example, PA to A1 means the probability for a site to contain nucleotide A at time 1 if it actually had A at time 0, which by the definition of the Jukes-Kender model is 1 minus 3 alpha. Similarly, we just show that PA to A bracket 2 is the square of 1 minus 3 alpha plus 3 alpha squared. In general, PA to A bracket T plus 1 is the sum of two parts, namely the situation that the site was also A at time t and the situation that it was something else at time t. The probability for the site to have A at time t is PA to AT, and we multiply it with 1 minus 3 alpha, since it does not mutate further from time t to time t plus 1. The probability for the site to be something else at time t is just 1 minus this PA to AT, and we multiply it with alpha since it mutates to A from time t to t plus 1. This recursive formula can be generalized to any x and y. Now, we solve this recursive formula to get a simple solution for PA to AT. The first step is to simplify the right-hand side by rearranging some terms. Then we use a trick here to subtract 1/4 from both sides. The reason is that we can then rearrange the terms on the right and end up with this formula that has a form highly similar to the one on the left, except that the time is changed from t on the left to t minus 1 on the right. And there is an extra multiplication factor of 1 minus 4 alpha. This means we can keep replacing the time unit by 1 before if we multiply the formula by an extra 1 minus 4 alpha. By doing it again and again, finally, we reach time step 1, and we already have the formula for it, which is 1 minus 3 alpha. Finally, by simplifying the formula, we get the final solution that PA to A bracket T is equal to 3/4 times 1 minus 4 alpha to the power t plus 1/4. The value of this formula can be easily computed, even for a large value of t. If we make each time step infinitesimally small, we can also solve the equation by turning it into a first-order differential equation. We will not go deeper into this topic here, but the solution to the differential equation is useful when we do not know the actual values of alpha and t, but only know the value of their product.